Hello, everybody. Welcome to Zurich. My name is Julia.
And I'm Thyla. And before we get started with the conference, we thought you'd give you a few Zurich survival tips, specifically how to order a beer in a bar. Now, Julia's German is much better than mine. So, Julia, how do I start by saying hello?
Well, actually, you need Swiss German because we're here in Switzerland. So my Swiss German is really not good. So we have an expert in the first row.
Thank you. Grüezi miteinander.
Okay, so everybody. Good job.
Perfect, right, off to a good start. Secondly, how do I say pardon me to get the barkeeper's attention? Julia?
Entschuldigung.
Okay. Let's try that. Entschuldigung. Good, okay. Very important. How do I say beer?
Bier.
Okay, that one's pretty straightforward. And then finally, to say thank you.
Well, the German version would be Danke, and the Swiss German version would be
Merci.
Good. All right, so now if you need to go into a bar in Zurich, that might save you this week. All right, so I'm going to hand over to Julia, who's going to tell us more about the stats.
Yeah, stats. So we have 732 registered participants to the conference, which is roughly 20 more than last year, and last year was already a record, so this year we have a record as well. Every student gets, on average, 2 regular attendees to mentor them, so we have a good portion of regular attendees this year. 43 countries. I stopped counting on Friday. Same for workshop participants. This was just crazy. We had very successful workshops at ETH with over 500 participants. Yeah. Okay. The venue, you have already found this room, so you saw most of it already. Just going to give you a quick orientation. So you see where you entered with the front desk. After the front desk, there's a hallway to the left. There's a sign, Gartensäle or something, and there you find track 3 and track 2. This is track 1. And this is essentially the downstairs area. There is the large foyer, which will be used to serve food later. So we're going to ask you also to move down if it's going to be very crowded up here with the food. So just move down. There's more buffet stations and more space down there. The upstairs venue has, we are essentially in the bottom left part here in the Kongresssaal. There is terrace space, maybe not today, maybe later today. Nice to use. You can reach this if you exit the track 1 room. You go to the right. There are some doors that you can use to get out on the terrace. Recommended. It has a very nice view over the lake and of the mountains. Let me see. Right. Also pretty nice is that we have another floor on top of this, which has kind of like a small gallery, which has nice seats and also power if you need to charge. You can see, you need to go somewhere there to the left. There are stairs which go up. You can check out the gallery. It's also perfect if you have to take a call or something, or want to, work on your Eurocrypt submission. Just go upstairs. Oh, can you go back because the special events? Straight that way, there's a small hallway and a small room, which is going to be used for special events. First one, I think, already today. We'll put up some signs to guide you there. Okay? Right, so food, I already said that we have 2 food areas. One is directly out here. The other one is downstairs, and just ask you to spread out. There's more food downstairs. Here in the food area, by the way, you also find our sponsor stands a bit to the right here. So you're very welcome to just get your food and check out the sponsors. There's a small bar to the left here on that side. It's called a Kongress Bar. You see it on the right-hand side. If you have a special diet, if you have any questions about the food, any concerns regarding allergies, please just go there. People with special diets should have already received an email about it, and this is just outside this room to the left, essentially. Okay, so because we are that many people and we didn't find a place in Zurich that is big enough to host a dinner, we decided to 3-track the dinner on the Zurich Lake. Essentially, we rented 3 boats. You find, if you registered for the dinner, so if you check the box that you want to attend the dinner, you find a ticket in your badge indicating the name of the boat. There's Panterei, MS Helvetia, and Genussboot. Please make sure you have your ticket on Tuesday night, because we will only let you on the boat with a ticket, because we have a restricted number of seats on each boat. Please do not swap your tickets if you have a special diet, because then otherwise we cannot guarantee that you get the right food. This is the only event where registered guests, so the +1s that you could add on a registration, where they are invited to join us. In that case, you should find 2 tickets in your badge. Okay, so these are the 3 boats, as I said, Panterei, Helvetia, and Genussboot. 2 of them, Panterei and Helvetia, they leave from Böckliplatz, which is just a very short walk from here. Panterei is the boat that people with special diets go on. And Genussboot is a slightly smaller boat which leaves from Bellevue, which is also just a short walk from here, and has fish and vegetarian. Okay, I didn't say the other ones. Okay, so there's a map where you have to go. You also find the location in the online program. There's a link with the Google Map location. And we also have this as a poster at the front desk, so don't worry about finding it. We also have this is the map for the other one, so you can see it's just a bit further. Can you click one more? Yeah, so we will also organize to just walk there with you. So this is the downstairs area. The front desk is the pink thing, and essentially for your boat, we will be holding up signs, and you can just, join us, and then we are going to walk together, leaving at 5:45 on Tuesday. 5:40. 5:45, leave it just after 6. Ah, okay.
Okay, so a few notes about the program. So as Julia mentioned, we have 3 tracks, and they're going to be happening in Kongresssaal, which is where we all are now, and Gartensaal 1 and Gartensaal 2, and those are downstairs. We also have some special sessions. Those are additional. Please look out for QR codes that are dotted throughout the venue if you want to find more information about those special sessions. Specifically, there's going to be Eurocrypt, which is happening this afternoon. The Women in Cryptography meeting is going to be happening tomorrow afternoon, Tuesday afternoon. The mentoring session for students will happen on Wednesday at lunchtime, and Eurocrypt is going to happen on Thursday during the coffee break. And all of these will be happening in Vortragssaal 2, which is just across the way from where we are now. There will be signs which will guide you to those. Okay, so if you need any help, there are people walking around that have a turquoise lanyard. These are part of the organizing committee, and they should be able to help you. Most people sitting at the front desk will have a turquoise lanyard, and you should be able to find people with turquoise lanyards at the front desk, but they will also be milling around the venue. Now, we do expect everybody to adhere to the IACR's Code of Conduct, but if you do experience any harassment or discriminatory behavior, please reach out to me, Julia, Alison, or Michelle. We are all here. And our contact details are on the website, but you can also use that QR code over there for even further contact options. Please just remember to respect each other at all times. Right, now to the thank yous to all the individuals and organizations that made this event possible. Firstly, to our program chairs, Marc and Gregor, thank you for all of your hard work, and to the entire program committee for putting a great program together. So let's thank them. Okay, next up, the organizing committee. As I mentioned, these are people with turquoise lanyards and a few other key individuals that have been instrumental in making Eurocrypt 2024 a reality. And specifically some special mentions really to Bertram Puttering, Brian Lamachia, and Kevin McCurley from the ISCR for all of their support, to Felix Gunther and Christina Horstakova for organizing the workshops, and to ETH for hosting those workshops for us for free. To Jonathan Bootle and Sebastian Thyla for a lot of behind-the-scenes work. Now, we really want to call out Sebastian here. He has done so much work to making this happen. So if you see this man, if you see his name tag, buy him a beer. And you now know how to do that in Swiss German. Also, we want to thank the IBM team for crafting over 800 badges and all of your dinner tickets. And also to Damian Steller, who ran Eurocrypt last year, for countless tips on how to Eurocrypt. But before we move on, we really want to call Sebastian up to give him a small token of our appreciation. But let's thank everybody on this slide. Thank you, Sebastian. Thank you so much. Okay. Okay, so just to point out that if you do have any basic catering questions, we do have a catering sub-team. So Julia, Simon, and Antonio will be available for you. And if they can't troubleshoot a question for you, they will be able to find somebody who can. But reach out to them if you have basic catering questions. Okay, then to all of our sponsors, without which the registration fee would have been even higher. So thank you to our platinum level sponsors and our gold level sponsors, and also to our silver level sponsors and our bronze level sponsors, and a special thank you to our dedicated diversity sponsors, and also to our travel stipend sponsors, who really made it possible to bring a diverse set of participants from all around the world to Eurocrypt in 2024. So thank you. Okay, and with that, please enjoy the conference and enjoy this wonderful city. So yeah, and I think we're going to hand over to the program chairs for the next session. Marc, Gregor.
Good morning, everybody. We are not going to say much more than for a normal session at this time, I think.
No, I don't think so.
No, welcome to the technical part of the show. And it starts with the awarded papers, which is a pleasure to start with Itai Dinur on tight indistinguishability bounds for the XOR of independent remnant permutations by Fourier analysis.
Yes, so maybe as a comment, so if you have questions at the end of the talk, so just line up to the mic so that people online can also listen to you. Thank you.
Me? Do you hear me? Okay. So thank you very much for the introduction. And let me begin. So many cryptographic primitives that we're using today are based on pseudo-random functions or PRFs. This includes, for example, encryption schemes, MAC algorithms, etc. However, in practice, these pseudo-random functions are typically implemented using block ciphers, which are pseudo-random permutations or PRPs, and this is simply due to performance considerations. However, the block ciphers or pseudo-random permutations are only secure up to the birthday bound of Q roughly 2 to the n over 2 queries, where n is the block length. So let's see an example. So let's consider the standard counter mode of encryption and assume we are implementing it using a block cipher E. So in this case, the advantage of any adversary in a chosen plaintext attack on the counter mode can be bounded using a simple hybrid argument. And what you get is basically a sum of two terms. The first term is just the advantage of the adversary in distinguishing the block cipher itself from a perfect random permutation using Q queries. And the second term bounds the advantage of an adversary in distinguishing a perfect random permutation from a perfect random function using Q queries. So the second term is exactly the birthday term, and it is equal to roughly Q squared over 2 to the n. Okay, and this is theoretical formula. However, it actually was shown that it can lead to a practical attack on TLS if you're using, for example, a block cipher with a block size of n equals 64. Now, if you're using AES with n equals 128, then this is perhaps less of a concern, but still, if you are encrypting a lot of data and you want to achieve a high security level, then you may still be concerned with this birthday term. And because of this, we may be interested in beyond birthday bound security. And this means that basically our goal is to design an efficient pseudo-random function that is secure way beyond the birthday bound of Q equals 2 to the n over 2 queries. And we want to do this using pseudo-random permutations, which are, in practice, will be implemented using block ciphers. Okay, and a very famous construction that achieves security beyond the birthday bound is called the XOP, which stands for XOR of permutations. So given two permutations, pi1 and pi2 on n-bit blocks, the XOP construction is defined as follows. So on query I, it just XORs the outputs of pi1 applied to I and pi2 applied to I. Okay, so this is how the XOP construction is defined. Now, as usual in the analysis of the scheme, we're going to assume that pi1 and pi2 are perfect uniform and independent permutations. In practice, of course, they are going to be implemented using a block cipher. Now, you can also consider a generalization of the scheme, where we are given an additional parameter r, and the generalization just outputs the XOR of r permutations. Okay, so this is a famous construction that's been analyzed first, I think, already in 2000 by Stefan Lux, and it has been analyzed in many papers since then, both in the single user and multi-user settings. And there are standard techniques that are used to analyze the schemes. One of these techniques is mirror theory. Another, which is a bit more recent, is the chi-square method. And with these techniques, the best known bound on the advantage of an adversary that tries to distinguish the XOP construction from a perfect random function using Q queries, the advantage was bounded as Q squared over 2 to the 2n. Okay, so now I'll describe the results of our paper. So in the paper, essentially, we prove tight bounds for the XOP construction for all of its variants, and we also extend the bounds to the multi-user settings. And all of the bounds that we prove are tight because they are matching attacks that were published some time ago by Patara. And our proof technique is based on Fourier analysis, which is quite different from the previous proof techniques, at least in the crypto community. Okay, so let's focus on the case of r equals 2, which means the basic XOP construction. So the bound that we get in this case, when the adversary uses Q queries, is Q over 2 to the 1.5n. And if you compare this to the previous bound that I described, Q squared over 2 to the 2n, then this bound is much better if you are above the birthday bound. And specifically, if you go all the way up to roughly 2 to the n queries, then the advantage using our bound is roughly 1 over 2 to the half n, versus a constant if you're using the previous bound. And this is an exponential gap. And as it turns out, the basic case of r equals 2 was actually already analyzed in 2017 by a mathematician, Eberhard, and he proved a similar asymptotic bound. It's actually a side result. It's an interesting side result in a paper on additive combinatorics that's not very well known in the crypto community, and it was pointed out to me by Samuel Neves after I put my paper online. Now, Eberhard also used the Fourier analysis to obtain his result. There are differences, technical differences between his proof and the new one, but they are kind of technical and details can be found in the paper. Okay, so what are the applications of this result? So let's, for example, consider counter mode. And if we replace the block cipher with the XOP construction, and now let's look at the new advantage bound that we get. And the second term in the advantage, we see that the birthday term is replaced with the term q over 2 to the 1.5n, which is, of course, much smaller. Okay, so in the rest of the talk, I'm going to give you a high-level overview of the proof for the basic construction with r equals 2. So the proof basically consists of 3 main steps. In the first step, we're going to bound the advantage of the adversary in the so-called Fourier domain in terms of the Fourier coefficients of the XOP construction. In the second phase, we're going to reduce the analysis to a Fourier analysis of the sampling without replacement distribution. And then the third step, we're going to bound the Fourier coefficients of sampling without replacement distribution. And I should mention that I'm going to, in the rest of the talk, I'm going to sketch only the first 2 steps. The third step is actually the most technical, and I won't have time to really discuss it, but details can be found in the paper. Okay, so let's again consider the XOP construction, the basic construction with r equals 2. So again, we are assuming that pi1 and pi2 are uniform permutations that are independent. Now, first, a simple observation that if you consider, for example, pi1 applied to a query I, that then the output actually does not depend on I. It only depends on the previous elements that were output by pi. Okay, and of course, for pi2, this is the same. And this actually means that the XOP, the output of the XOP construction does not really depend on the queries of the adversary. And therefore, it makes sense to define the output distribution of the XOP construction. So the output distribution of the XOP construction, we're going to denote it by phi, and it's going to take as a parameter some value x. So x is just is a value from the domain of q elements from 2 to the n. Okay, and the value of phi on x is just the probability that the XOP construction on Q queries outputs X. Okay, so this is a standard distribution function. And we're also going to denote the uniform distribution function on Q and bits by U. And it is well known that the advantage of any adversary against the XOP construction is bounded by the statistical distance between the distribution mu and the uniform distribution u, which is essentially half of their L1 distance. Okay, and now what we're going to do is we're going to switch to the so-called Fourier domain. And for this, we're going to apply the Cauchy-Schwarz inequality and then use the Parseval's theorem. So I'm not going to go into the details of this, although it's relatively standard. And what we get after doing this, you can see on the right-hand side, we get some expression. So I'm going to tell you what this expression means. So you can see that we're summing over all kinds of alphas here. So an alpha is basically a mask or a linear expression over the Qn bits of the domain. And a phi hat on alpha is called the Fourier coefficient of phi on alpha. It is just the bias of the inner product between alpha and x over F2 where x is drawn from phi, meaning it is sampled by the XOP construction. Okay, formally the Fourier coefficient is defined using the formula that you see here. So essentially what we want to bound now is as we're considering the sum, considering all alphas, meaning all linear expressions, and we're summing over the bias of the sample on this expression squared. Okay, this is essentially what we have here. So just to give you a bit of intuition, let's assume for a second that we're considering the uniform distribution. Okay, U, on the Qn bits. So in this case, if we fix some linear expression, then we know that it's going to be unbiased, meaning that the probability that it evaluates to 0 is equal to the probability it evaluates to 1. And this means that all the Fourier coefficients of the uniform distribution that are non-empty will be equal to 0. They are unbiased. And therefore, if you, using the same formula, calculate the statistical distance between U and itself, then what you sum over is just zeros, and then you get 0. Of course, this is what you expect, because the statistical distance is indeed 0. But of course, here we're not, the Fourier coefficients of phi are not going to be 0, but we really want to prove that they are very close to 0, in some sense. Okay? Okay, so moving on. So next I'm going to define a new distribution, which is, I'm going to denote it by mu. It's going to be the distribution of sampling Q elements from F2 to the n uniformly without replacement. So now we recall how this distribution phi was generated, right, by the XOP construction. So it is actually generated by XORing two independent mu samples. And this actually, if you look at it, it corresponds to just a convolution. So a convolution formally is defined using this formula. So a phi on x is just mu convolved with itself on x, and it is equal to the formula shown here. And what's nice about convolution is that in the Fourier domain, convolution corresponds to multiplication. And we have this, therefore, we have this very basic theorem which says that phi hat on mu is equal, on alpha, sorry, is equal to mu hat on alpha squared. Okay, because again, convolution in the Fourier domain corresponds to multiplication. And now if we go back to the expression that we want to bound and plug this into this expression, then actually what we want to bound, if we look inside the square root, what we are trying to bound is the sum over all non-zero alpha of mu hat on alpha to the power of 4. And in the paper, what we do is we indeed analyze this mu hat on alpha, which is, as I said, is a bit technical. And then we are able to bound this expression. But I think what I already showed you is kind of motivates, the use of Fourier analysis, because we started in analyzing and trying to analyze a relatively complicated cryptographic scheme, but we reduced it to kind of a clean mathematical problem of analyzing fundamental distribution of sampling without replacement. So this is as I said, it's kind of a clean and very nice mathematical problem that it's not directly related to cryptography. Okay, so let me conclude the talk. So in this work, we proved the tight indistinguishability bounds for XOP constructions, actually for all of its versions, both in the single and multi-user settings. And in the future, so the proof relies, as you saw, heavily on Fourier analysis. And in the future, I think it will be interesting to use similar type of analysis to improve the bounds for permutation-based PRFs. And actually, I think it is maybe even more interesting to design new permutation-based PRFs, which are both efficient and have better security bounds using similar techniques. Okay, and that's all. Thank you.
Thank you very much, Itai, for the very nice work and a nice talk. Questions?
Quick question. Do you have restrictions on queue? So how close to the end can you get?
That's an interesting question. So what I proved in the paper is that you can go to Q roughly 2 to the n over 2, like half of the domain size. But you can go further. I think you can even go up to all domain size minus 1. You cannot go to the entire domain size, because if you XOR all the queries, then the answer will be equal to 0. But I think you can go just one query below that, and it still works. But it's not easy to prove. It's more difficult.
Hello, so great work. So I want to ask like a meta-scientific question about like the rediscovery of the work, like the mathematician. What kind of, was it done concurrently? What surprised you? What did you learn? Like, I think that a bit more information on that would be great. We'd be very curious.
It was a bit surprising to me because I don't know how this happened, but apparently the crypto community, including myself, were not aware of the previous work. It was done in a completely different field, additive combinatorics. I mean, these are serious mathematicians, of course, and they approach the problem. They had, I mean, very different motivation, and they were trying to I think, count traversals and lattice squares, and they approach it from a completely different angle, and yeah, it just happened. I don't know. I mean, if you were not aware of these works previously, then it's not easy to find it. So I don't have much to say beyond that.
So this is kind of a question that about something that you mentioned, not directly to your work. You said that like PRPs are much more performant than PRFs. Like, I don't have an intuition for that. Like, it seems like you have a much bigger design space if you're not restricted to a permutation.
I'm not sure the design space is really like the right way to look at it. So I try to give you intuition. So if you consider AES, I mean, we know that AES is extremely fast, and also it was, it's very. There are specific hardware that is, designed to make it even faster. And we know how to design block ciphers. It's like it's very easy because every step you kind of perform a simple simple transformation on the space, and which is a permutation, and it's invertible. And then that's kind of how we build block ciphers. But when you try to build pseudo-random function, then it's not clear how it would work. How would these incremental steps would work? Because if they're non-invertible, I mean, then it seems that you're losing something every step, and then it's not very clear how this would work. So I don't know if this answers your question, but
yeah, it does. Thank you.
Yeah.
Thank you very much for the questions. Thank you very much, Itai. one question to the technical stuff. It would be nice if you don't show these slides during the questions. I think it's just leave the slides of the talk. Thanks.
Okay, so second talk of this session. So it also received the Best Paper Award. The award was given to Pierrick Darbois, Antonin Leroux, Damien Robert, and Benjamin Wiesolewski for their work on SQI Sign HD. And Pierrick will be giving the talk.
So, do you hear me? Do you hear me now? Yeah, okay, thank you. Thank you very much for this introduction. So right now I will talk to you about SQI HD to bring new dimensions in cryptography. This is a joint work with Antonin Leroux, Damien Robert, and Benjamin Wiesolewski. And I would like to give special thanks to Luca De Feo for his help all along this project. So SQI HD is an isogeny-based scheme. So if you have already used the Wi-Fi, you already know that isogenies are alive. And here is proof of this. So I will first talk to you a bit about isogenies and the Turing correspondence to see how they relate to quaternions. Then explain how we can make this Turing correspondence more effective, more efficient, with higher dimensional isogenies. And finally, see an application to this to improve the SQI signature scheme and make SQI HD. So first, let's talk about isogenies and quaternions. So if you are not familiar with isogenies, what you should know is that it's just a map between two elliptic curves, which has the nice property of being a group homomorphism and being concretely expressed by rational fractions. If we want to measure an isogeny, we have an invariant, which is its degree, which in most cases is just the cardinality of the pre-image of any point. If we have an isogeny from E1 to E2, then we have another isogeny from E2 to E1, which is called the dual isogeny, which is not an inverse, but still has nice properties. And one of those properties is to preserve the degree. So we can compose isogenies, of course, and the composition of different isogenies has degree, which is just the product of all the degrees of individual isogenies. Conversely, if we have an isogeny whose degree is big and smooth, then we can decompose this isogeny into a chain of smaller degree isogenies. And this is very convenient for cryptographic application because we have algorithm to compute this isogeny chain given the kernel in polynomial time by successively computing every step of the chain. So now let's talk a bit about quaternion and how they relate to isogenies. So quaternion algebra is just a Q algebra of dimension 4, which is non-commutative. And in the context of cryptography, we work with quaternion algebra ramifying at a prime p and infinity, which are given by the expression here on the slides. We could also consider orders in quaternion algebras, which are just maximal rank, full rank lattice, which are also subrings. So why do we care about this? It's because elliptic curves have an endomorphism ring, which is made of all isogenies going from E to itself. And in the case that is interesting for us, which is the supersingular case, this endomorphism ring is a maximal order in the quaternion algebra ramifying at P and infinity. And we actually have a correspondence between the world of supersingular isogenies on the one hand and the world of quaternion on the other hand that is useful, as we shall see later. So this correspondence starts with supersingular elliptic curves to which we associate maximal order in the quaternion algebra given by their endomorphism ring. But it doesn't stop here. if we have an isogeny between, let's say, E and E prime, we can associate to it an ideal, which is a left ideal for the endomorphism ring of the domain and a right ideal for the endomorphism ring of the codomain. If we have two isogenies from the same domain and with the same codomain, they correspond to equivalent ideals, that is to say, ideals which are equal up to multiplication on the right by a quaternion. The dual isogeny corresponds also to the conjugate of the associated ideal. Let's say that we have a conjugation map on the quaternion which extends the one of the complex numbers. And if we have the product of two isogenies, they correspond to product of ideals. And finally, we can measure the size of ideals by their norm, and this size, the norm, corresponds to the degree of the isogeny. So how can we make it practical? How is it useful to cryptography? It's actually useful when we have two elliptic curves of known endomorphism ring, and we want to find an isogeny between the two. So let's say we have E1 and E2, two supersingular elliptic curves of known endomorphism rings O1 and O2. First, we can find a connecting ideal between O1 and O2, which is a left ideal for O1 and a right ideal for O2. This ideal is not smooth. It does not have a smooth norm in general, so it's impossible to translate directly into an isogeny, because remember, we know how to compute only smooth degree isogenies, at least for now. And so how do we proceed? We find an equivalent ideal to this ideal, which has smooth norm, and we translate it into a smooth degree isogeny. So this is polynomial time. And this has a cryptographic interest because this becomes a hard problem when either one of the endomorphism rings of E1 or E2 are unknown. But the drawback of this is that it becomes slow in practice because of the steps in red, especially the fact that we need a smooth norm ideal makes the ideal very big, and when we translate it to an isogeny, it's costly because the isogeny has big degree. So that's why we introduce higher dimensional isogenies in the hoping to make it more efficient. So higher dimension isogenies were already introduced in Eurocrypt last year in the SIDH attacks. So it proves to be fruitful because those papers already had best paper awards. And so what is it exactly? So if we have an isogeny between E1 and E2, and whose degree plus a sum of 2 square is a big power of 2, then we can embed this isogeny sigma into a dimension 4 isogeny, which is represented by this big matrix. So if you want to know how this monster works, you see that it acts on points as a matrix vector product. And this big isogeny in dimension 4 can be computed once we know the image of sigma on the 2 to the e torsion. Because once we know sigma on the 2 to the e torsion, we can compute the kernel of this big isogeny. And once we know the kernel, we can compute this isogeny F into a chain of smaller isogenies, as we would do in dimension 1 for smooth degree isogenies. And everything can be done in quasi-linear time. And once we have done it, so once we have computed F, it's convenient because we know how to evaluate F, of course, and so we know how to evaluate sigma by this formula. So what we obtain is an algorithm that gives an isogeny of bounded degree such that 2 to the e minus the degree q can be written efficiently as a sum of 2 square. We have an algorithm that takes the image by torsion points of the 2 to the e torsion by sigma, and that returns an algorithm to evaluate sigma on any point in polynomial time. And how can we make use of that in the context of SkiSign? So in SkiSign, the underlying problem is that we have an isogeny between E1 and E2 the endomorphism rings of E1 and E2 are known, also the ideal corresponding to this isogeny. And we want to find another isogeny between E1 and E2 that is completely unrelated to it. And so the way we proceed in SkiSign was just to find an equivalent ideal, which is random on of smooth norm, to the first ideal that we have, the ideal of phi, which had big norm, and then to translate it into an isogeny. But it was slow. In SkiSign HD, we relax this constraint of smooth norm. So the norm is not smooth anymore, but it's much shorter. And we hope that it's more efficient to translate now this ideal into an isogeny. How we proceed? We use some tricks to evaluate sigma on the 2 to the e torsion using the isogeny that we already have. And then the information given by the degree Q of this isogeny and this image on the 2 to the e torsion is sufficient to represent it. And then we are able to compute this dimension 4 isogeny embedding sigma if we want to check that sigma is indeed what it's supposed to be. So how can we make use of that in SkiSign HD? So SkiSign HD is a signature scheme based on a Fiat-Shamir transform of an identification protocol. So right now I will recall how this identification protocol works. So we start with a public elliptic curve E0 and of known endomorphism ring. And we publish EA, which is another elliptic curve, which is supersingular. And we know a secret isogeny between E0 and EA. And suppose that I want to prove to someone that I know this secret isogeny. So how can someone verify my claim? They will ask first to me to commit a supersingular elliptic curve E1, which is related to E0 by another secret isogeny. Then they will challenge me with another isogeny between the public key and another elliptic curve E2. And I will have to answer with a response isogeny between E1 and E2 to prove my knowledge of the secret isogenies without revealing any information on the secret. So especially this sigma will have to avoid passing through psi and tau and phi. And the verifier will accept it if sigma is correct. So in SkiSign, we were just sending sigma directly as a big chain of isogenies in dimension 1. And in SkiSign HD, we proceed differently by sending just the degree and its image by torsion point. And this is actually very fast. So we have a fast signing procedure. For the verification, though, we still have to check that sigma is what it's supposed to be. So to compute this higher dimensional isogeny representation by computing this big F that I introduced just previously. This seems frightening to have to compute dimension 4 isogenies, but in practice we have a proof of concept implementation in SageMath that runs below 1 second for NIST-1 security level. So it's still promising, and we hope we will improve it even better. So I will now conclude my talk with just a comparison between SkiSign and SkiSign HD to see how this new scheme improves it. So far, I haven't talked about security, and the security of these schemes relies especially on proof of the zero knowledge property, the fact that the response doesn't leak any information. And in SkiSign, the security assumption to prove the zero knowledge property was quite ad hoc. It relies on heuristic assumptions on the distribution of the response. And now in SkiSign HD, our heuristics are much simpler and they look a bit nicer. For scalability, we also have an improvement because we can reach higher security level without searching for prime P, defining the characteristic of our base field, which are costly to find, like the scalability is better for that reason. The signing time is much, much improved. The signature size is even more compact even if it was already very competitive with Keysign. And the only drawback is the verification, but with a lower level implementation, we hope to improve it by 2 orders of magnitude. Thank you for your attention. I'm now ready and happy to answer your questions.
Any questions?
Comments? Maybe I can ask one. Do you have planned to deploy the scheme or not?
Sorry,
Are there some plans to deploy the scheme in practice?
Right now, we don't have precise plans about that. I think we still need to have a C implementation of the verification first. I would say we also have competition because there are attempts successful attempts to transform this verification from dimension 4 to dimension 2. And to reduce the cost of verification. So maybe this dimension 2 version of Keysign HD, there are different ones, could be deployed in the future.
Any more questions, comments? No? Okay, so thank you, Pierrick, and your co-authors.
And then the last talk of this awarded paper sessions is après-ski. I hope it's correctly pronounced. Yes. Extra fast verification for SQI signing using extension field signing. And the paper is by Maria Corte Real Santos, Jonathan Komada Eriksson, Michael Meyer, sorry for all the bad pronunciation, Krein Reindas, and the talk is given by Jonathan.
Yes, thank you for the introduction. You can all hear me, or? Yeah, it's very hard because the speakers are pointing. Yeah, okay. Either way, yeah, thank you for the introduction. I'm here to present après-ski, and as was mentioned, this is joint work with Maria Corte-Real Santos, Michael Meyer, or Michael Meyer, and Krein Reinders. If you're all a bit tired of Keysign now as well, I've also included a bunch of these slides includes a bunch of nice mountain pictures, and half of them are from Norway, the other half are from here in Switzerland, so you can discuss with the person next to you and try to figure out whether it's Norwegian mountains or Swiss Alps. Or you can pay attention to the talk as well. But, yeah. This talk is really more about the classic Keysign version, no fancy higher dimensional stuff. And in the classic version, as we just heard from Pierrick, the original Keysign really had super fast verification, or relatively fast at least, and very simple verification, and small signatures, but the huge drawback of having a very slow signing time and fairly complicated signing procedure. But then the idea in this paper is basically that, okay, maybe we can accept that signing is slow and complicated, because for a lot of signature applications, this might be okay if you have some kind of long-term signature thing where one party is supposed to sign a message once, and then a bunch of people verify this many times, right? So then maybe you're okay with signing being a bit complicated and slow, as long as verification is as fast as possible. And that's really our goal in this project, was to really push the parameters of Keysign to make verification as fast as possible. So just to recall, Pierrick basically already explained this, but in the classic Keysign version, we have some kind of curve EA with a known endomorphism ring that's really kind of given by a known isogeny from a curve E0, where E0 is known, or has known endomorphism ring. And then the commitment is just a random isogeny to another curve, E1, and then you send E1 to the verifier. The verifier gives you a challenge isogeny back, and then your response, what you try to do to answer this challenge, is to connect EA to E2, because as PIX said, all of this information that you have, basically, you want to prove that you now know both. Or you want to kind of intuitively prove that you know the endomorphism ring of EA. And that allows you to compute this response isogeny. So since I'm going to talk mostly about like verification and how the parameters affect the verification, we're really going to focus on like this part of SkiSign in this talk. So a bit more detailed, when you use like don't use this higher dimensional technique, but the classic like KLPT approach to computing the response, you end up with like a really long 2 isogeny. So as you can see, this one has like degree 2 to the 1,000. And then this is kind of an issue because we're really like always using explicit points that generate subgroups that are going to be kernels of our isogenies. But the problem then is that like you can't fit 2 to the 1,000 in a prime of size or on a curve that's like defined over a prime of size p square. No, prime of size, yeah, 2 to the 2 lambda. So essentially what you have to do is you have to like split up this isogeny in parts and kind of like translate it part by part. And like it's not so important what's going on the right for this talk, but I just wanted to show like essentially what you need is that you need points of order 2 to the f, where f decides like each step length, and then you need some t, where t is odd and smooth. So you can really, it's really like the thing on the left here that you should focus on. Like, if you want to then stay over fp square, which is kind of like what we do in original SkiSign, then you really need to fit like a lot of smooth things inside p+1 and p-1. And this generating primes that has this particular property is actually quite difficult. And yeah, there even exist like papers just trying to find these type of primes. But yeah, so and the intuition here is that the more 2 power you put in, the harder it's going to get to find the t that's also smooth and fits in there. So okay, so let's go move on and see how like concretely a bigger power of 2 really makes verifying easier. So essentially, when you're given a SkiSign signature, what you're essentially given is a bunch of points that generates these steps, right? So I'm kind of lying. This is like an uncompressed version, but whatever. Let's look at that simpler case. So what you do is that you essentially just take like these points and compute the corresponding isogenies step by step until you reach E2. And then since it's like a Fiat-Chaumy transform of an identification protocol, you also need to recompute the challenge and check that this indeed verifies what you're trying to verify. Let's forget about the challenge for now. But my whole point was that, okay, my claim was that if we increased f, like the power of 2, then there's fewer steps, and that's better. And you can clearly see this in like the uncompressed case, because then the signature becomes much smaller. It's suddenly way fewer points to care about. And as I said, this is not really the case in practice, because we have like this compression, so the signature doesn't get any smaller. But decompressing each part takes a bit of time. And that essentially means that the fewer points we have, the faster the verification becomes instead. Yeah, so that's kind of like the intuition for why we want to push this 2 power up, and to see like a bit more concrete how this corresponds to a bigger power of f. You can really like create kind of signatures for arbitrary powers of f in your prime, and then you can really see that like the signing times goes down pretty quickly with increased f. Okay, and there are actually more benefits, not just like straight up inputting a different prime, but a larger power of f actually gives you access to a lot of other optimizations. Like one thing that's not even discussed in the paper at all is just that finite field arithmetic is faster in that case. But actually, like lots of the stuff with decompressing the points and stuff, like this requires generating kernel or torsion basis and the kernel point from this. All of this you can apply kind of like known tricks, and and it all becomes faster. And in addition, you have all of these like side speeds trade-offs, right? If you're okay with, maybe say you want to fit your signature into something, maybe you're okay with increasing the size a little bit. And then a bigger power of f is again positive because it essentially like lowers the amount you have to increase your signature with, like size, for the same gain. So in the most extreme case, to like really visualize this, we can consider these uncompressed signatures that I mentioned. And then the compressed NIST signatures for the parameters that are used in SkiSign in the NIST submission, it would be like 177 bytes. But if you were to give an uncompressed version, it would almost be 1,000 bytes. But in our version, if you like push F to the most it can be, it's only like roughly doubling the signature size. Okay, so yeah, if we look at all of these improvements together, you can really see that we can really push the SkiSign signature to be super fast. Yeah, concrete speedups are given here, comparing with the NIST submission. But yeah, everyone already knew this, that bigger F would be better. So this was really just like motivation. But the question is, how can you like increase this F or increase like the powers of 2 inside of your prime? Because generating these primes were pretty hard. And the trick we do then is that essentially, if you look back at this picture, like the reason it's so hard is because we have this huge power, this huge smooth part T that we want to fit inside of these primes. But this requirements really comes from the fact that we don't want to use points that are defined over more than fp square. But okay, maybe what if we like drop this requirement and allow like kind of getting points from higher extension fields? Then that means that we don't care about this requirement anymore, and we can, in a sense, like arbitrarily push the powers of 2 up to fill all of p plus 1, for instance. But at the cost of then having to go to higher extension fields to compute these T isogenies. So let's take another look at like where these T isogenies or the computation of these. So as I said, it's really part of like the translating this long 2 isogeny to an to ideal of to high 2 norm to its isogeny. It really requires these like T isogeny computation stepwise when you're doing the non-HD technique, right? The classical KLPT based technique. And then, as Pierre said, we do this by computing L isogeny sequentially, but like the really like magical property about supersingular curves is that even though the kernel points might be defined over huge extensions of fp square, the isogeny itself is always going to be defined over fp square, or it's possible to make it defined over fp square. So this means that we can kind of like work with points that are defined over multiple field extensions at the same time, while never having to like go to an extremely large extension. And yeah, to compute this chain of this change of Li isogenies, this T isogeny, it's essentially like 4 different cases where we use like different algorithms, or we implement at least 3 of them. But so the worst case is this situation, because like you have one point that's defined over one field, and you generate the isogeny corresponding to that point, and then you want to push other points that are defined over like completely kind of like unrelated fields through this. So like the usual way to do this in isogeny-based crypto is you use this value formula, as it's called, but that would in this case require working in like the compositum of these 2 fields, so like the smallest fields where both points are defined over, and that can be like really, really huge and super costly. So what we instead do is we use this magical fact about supersingular curves, and we compute like explicitly the rational polynomial that defines the isogeny given by one point. So you take your point over fp2k, you get some polynomial over fp2, and then you can take your point over another field and just evaluate it in this polynomial. So you never have to go to like the compositum. Okay? But there are other cases, for instance, when the fields are actually contained in each other, you can again use value if the degree is small, or this asymptotically better square root value if the degree is bigger. And finally, there's also like another paper recently that, or kind of recent, that also considered this problem of computing rational isogenies from irrational points. And then for some like combinations of where the kernel point is defined and the point you are evaluating is defined, I think K and P should be switched there actually, but it doesn't really matter. Then you can essentially, it all comes down to just computing norms over fp square or fp, yeah, where the point you're evaluating is defined. No, fp square, sorry. Yeah, so you might use, so the point here is just to show that there exists a lot of different techniques when you're computing these rational isogenies from irrational points, and it's quite complicated to figure out exactly how to optimize it, and we don't really do it. But we just show that like a simple way of doing this kind of will be at least like not terribly much slower than what is already done in SkiSign. So as a concrete example, we give these two primes here that have like, the first one requires verification in 7 blocks, and the second one requires only 4 blocks. And then you can see on the right here which field extensions we need to work with when we're working with different Li torsions. And then we do make like a proof of concept implementation of the signing also. And if you look at the timings, these are not very impressive. But the point here is just to show that they kind of like, compared with just putting in the usual SkiSign parameters into the same implementation, it seems to not give such a slowdown. So of course this requires a proper optimized verification to really verify. And there is some early work that's kind of showing that it's promising. It's probably going to be a small slowdown, or a big slowdown, but it's still going to stay within the same order of magnitude at least in signing. And as I said, that was maybe something we were okay with accepting if we could get faster verification. Yeah, so to read this table, it's like the first prime is of course or not of course, but that's the NIST prime. And there you essentially always use value or square root value, right? But for the other ones, we do require these like a bit more slower ways of computing the isogenies, but yeah. Okay, I think that's all I had. Here are all the answers, by the way, for where the mountains were from. So thank you, and I'd be happy to take any questions.
Thank you very much. Other questions?
Okay. If you had access to some dedicated hardware,
yes.
What operation would need to be implemented to further speed up the verification?
For verification?
Yeah.
Well, you need FP square arithmetic, essentially. And so you don't need to do any higher, that's an important point actually. Like for verification, you don't need to do any higher extension field arithmetic. Everything for the verifier still happens over FP square. So you only need FP square arithmetic and like 2 isogeny formulas, essentially. And then like the required things for point compression, which are some like standard elliptic curve additions and point generation and so on. Yeah. And the isomorphism of curves, but that's, yeah, okay. Yeah.
Okay. No more questions? Then let's thank the speaker again. And we have a coffee break now. And just, yeah, a coffee break for half an hour, 45 minutes, I don't know.
Coffee break.
Coffee break.